best case would be trees that look like this one. This is a perfect binary tree in which all of the paths have the same length. That's logarithmic in the number of nodes in the tree. And even if we couldn't get the tree to be perfect, we want a shape approximating this perfect binary tree. Well, here are some strategies for achieving balance. In general, what we're going to do is strengthen the rep invariant to require balance and modify insert to make sure that rep invariant holds so that we get the balance. There are a few well-known data structures for balanced binary search trees. One of them is the 2-3 tree. This was actually invented by our own Professor John Hopcroft. In a 2-3 tree, all paths have the same length. That's guaranteed by storing either 2 subtrees at each node or 3 subtrees at each node. So that complicates the representation type a little bit, as well as the algorithms. A little bit more relaxed of a rep invariant than that is maintained by an AVL tree. In an AVL tree, the rep invariant says that the length of the shortest and longest path from any node differ by at most 1. So unlike 2-3 trees, it doesn't have to be exactly the same. There's a little bit of discrepancy allowed, but not much. They differ by at most 1. Actually, the OCaml standard library, in its tree implementations, uses a variant of AVL trees in which the length of the shortest and longest paths is allowed to vary by at most 2. So that's even more relaxed of a rep. Finally, a red-black tree has an even more relaxed rep invariant, which says that the length of the shortest and longest path from any node differ by at most a factor of 2. So the longest path could be twice as long as the length of the shortest path in the tree. But it turns out that's good enough to achieve balance and to get us logarithmic time operations.